In this lesson, we will look at the sources of air for an aircraft's cabin air conditioning system, and we will examine the methods used to maintain the air at a satisfactory temperature. We will begin, however, with a short review of the makeup of the atmosphere, to explain the need for air conditioning and pressurization systems. Modern jet airliners cruise at high altitudes, up to 43,000 feet. The advantages of high-altitude flying are greater fuel efficiency, higher speed, and, on most occasions, the aircraft will be above any bad weather. The disadvantages are that there is insufficient oxygen to breathe, and the air is extremely cold. In a standard atmosphere, the temperature drops at a rate of 1.98 degrees per 1,000 feet up to the tropopause, which is at approximately 36,000 feet, or 11 kilometers. This means that on a standard day at 31,000 feet, the outside air temperature will be a chilly -46 degrees Celsius. The atmosphere is made up of 78% nitrogen and 21% oxygen, with the other 1% consisting of various trace gases. The pressure of the air at sea level on a standard day is 14.7 pounds per square inch, or psi. So the partial pressure of the oxygen will be 21% of 14.7 psi, which is 3.08 psi. The table here shows the air pressure drop with altitude and the consequent reduction in the partial pressure of the oxygen. Below 10,000 feet, the body can cope with the reduction in oxygen pressure with no harmful effects. Above this height, the effects of hypoxia begin to become apparent, although passengers sitting and relaxing will suffer few noticeable effects below 15,000 feet. Aircraft air conditioning and pressurization systems limit the maximum cabin altitude to 8,000 feet, with a cabin temperature of about 20 degrees Celsius, thus providing a comfortable environment for the crew and passengers without the need for oxygen, except in emergencies. The provision of air from a large gas turbine-engined aircraft's air conditioning system is subject to regulatory requirements, governing both the amount and the quality of the air to be provided. These requirements are laid down in the EASA Certification Specification for Large Aeroplanes, CS25, Book 1. To summarize the regulations, each passenger and crew compartment must be ventilated, and each crew compartment must have enough fresh air, but not less than 0.28 cubic meters per minute, or 10 cubic feet per minute per crew member, to enable crew members to perform their duties without undue discomfort or fatigue. Carbon monoxide concentrations must not be more than 1 part in 20,000 parts of air. Carbon dioxide concentration during flight must not exceed 0.5% by volume in compartments normally occupied by passengers or crew members. Most modern gas turbine-engined aircraft have a bleed air system, which takes hot pressurized air from the engine's compressors and feeds it into the bleed air duct. The air comes primarily from a low-pressure source, but it may be augmented by high-pressure air. On the ground prior to engine start, air may be supplied by an auxiliary power unit. One of the primary uses of this air is to supply the charge air for the aircraft's air conditioning system. Since the bleed air supply is always at a higher temperature than that required for passenger comfort, it needs to be cooled before use. The cooling is done by the air conditioning pack. In order to provide redundancy, there are 2 or more packs, fed from different sections of the bleed air duct. The bleed air flow into the air conditioning pack is controlled by a pack flow control valve. Closing this valve will shut off the airflow and close the pack down. In many installations, this valve modulates to supply a constant mass flow of air to the pack, or in some systems, there is a separate mass flow controller. Most air conditioning packs use an air cycle machine, or ACM. The machine uses the principle of energy conversion and surface heat exchange for its operation. There are three basic types of air cycle machine: the turbo compressor, or bootstrap, the brake turbine, and the turbo fan. We will now look at each of these in turn. Of the three, the turbo compressor or bootstrap is the most popular air cycle machine in current use. It is used where the pressure of the bleed air is relatively low, as in the case of aircraft using high bypass ratio or small turbo propeller engines. It consists of two heat exchangers, both using ram air as their cooling medium, and a rotating turbine and compressor arrangement. The turbine assembly is sometimes referred to as the turbo refrigerator. The low-pressure bleed air, or air from a blower, is pre-cooled in the primary heat exchanger. Although the heat exchanger is very efficient, it can't cool the charge air down to a temperature lower than that of the ambient ram air, which in some situations may be as warm as 40+ degrees Celsius. The cooled bleed air then has its pressure and temperature increased by the compressor. Between the compressor and the turbine is the secondary heat exchanger, which serves to remove from the air much of the heat generated by the compressor. The pressure in the air is then used to drive the turbine. This removes the energy from the air and causes a large temperature drop. The output air temperature from the unit can be as low as 2 degrees Celsius. In order to provide sufficient airflow across the heat exchangers when the aircraft is on the ground, or at low speed in the air, a fan is provided. This fan is normally driven by the turbine, but in some cases it may be electrically or pneumatically operated. The ram air inlet and exit doors control the flow of cooling air through the heat exchanger. Their positions are controlled automatically by signals from the temperature control system. They are normally held open for maximum cooling on the ground and at low speed and low altitude. After takeoff, once the flaps are retracted, the doors will modulate as required to maintain the required pack outlet temperature. In some systems, they are automatically closed during takeoff and landing, to prevent debris damaging the system components. As the aircraft climbs, the outside air temperature cools, allowing the heat exchangers to become more effective. The temperature control valve allows hot bleed air to be added to the cooled air in order to maintain a comfortable cabin temperature. In the brake turbine system, the bleed air pressure from the engine needs to be considerably higher than the pressure required by the bootstrap system. The charge air is supplied directly to the turbine via a heat exchanger. The turbine drives the compressor, which takes in low-pressure ambient air and expels it through a restriction. This causes a back pressure on the compressor, which in turn puts a load of brake on the turbine, hence the name, and provides the energy conversion which removes the heat from the charge air. Some installations feed the output from the compressor into the ducting downstream of the heat exchanger to increase the airflow through the heat exchanger by jet pump action. This system is lighter than the bootstrap system, but unless the jet pump installation is used, it cannot be used for cabin cooling when the aircraft is stationary. The fan turbine, or turbofan system, is a refinement of the brake turbine unit, in which, instead of a compressor, the turbine is coupled to a fan of sufficient capacity to draw the required volume of cooling air through the primary heat exchanger. Therefore, the unit is not dependent on ram air for its operation and can be operated on the ground. The general design of the unit is such that it is extremely light and compact. The engine delivery pressure must be higher than for the other systems, and the turbine must be capable of higher speeds to achieve the necessary pressure drop. That is the end of the lesson. These are the main points that you should now know and understand. The charge air for a modern airliner's air conditioning system is supplied from the engine's compressors. Normally the low-pressure compressor, but in some circumstances the high-pressure compressor may be used. On the ground prior to engine start, air may be supplied by an auxiliary power unit. The temperature and the pressure of the air are controlled by the air conditioning system. The bootstrap is the most common type of air cycle machine. In this system, the charge air is first cooled in the primary heat exchanger. From there it passes to the compressor, where its temperature and pressure are raised. The purpose of this is to ensure an adequate pressure and thus temperature drop across the turbine. From the compressor, the air then passes through the secondary heat exchanger, reducing its temperature again. The air is now used to drive the turbine, which in turn drives the compressor. The pressure drop across the turbine produces a large temperature drop. The pack cooling fan is used to supply the heat exchangers with cooling air on the ground and during low-speed operation. In this lesson, we will look at the other components, which along with the air conditioning packs, make up an aircraft's air conditioning system. We will then examine how the air temperature is controlled and how the air is distributed throughout the aircraft. We will finish off by having a quick look at a vapor cycle air conditioning unit. When operating on the ground or at low altitude, the charge air entering the air conditioning pack may be very humid. When the air is cooled, this humidity will condense out as water droplets. In order to prevent it raining on the passengers and crew, a water separator is fitted in the pack downstream of the turbine of the air cycle machine. The water separator consists of two parts: a coalescer and a series of collector tubes. When the air leaves the air cycle machine, the water will be in very small droplets, in the form of a fine mist. The purpose of the coalescer is to increase the size of the water droplets. It consists of a filter, normally of coarse wire gauze. The water droplets come together on the gauze, forming larger drops before they are carried through to the second stage, where a swirl is imparted into the air. The centrifugal force throws the water drops outward. When they strike the collector tubes, they run down to the bottom of the case and exit via the water drain. The relief valve will open to safeguard the airflow to the cabin should the coalescer become blocked with ice or debris. The water separator does most of its work in low-altitude, humid conditions. However, at the high cruising altitudes used by modern transport aircraft, the air is very dry. When operating at high altitudes for long periods of time, it may be necessary to increase the moisture content of the conditioned air from the 1 to 2% relative humidity of the ambient air to a more comfortable level. The component used to do this is the humidifier, a typical example of which is shown here. The water tank contains drinking water. It is pressurized by bleed air from the engines. This tank is usually referred to as the potable water tank. The water jet is fitted in a Venturi tube downstream of the water separator in the conditioned air duct. Bleed air is also fed into the jet. This and the reduced static pressure of the dry air caused by the Venturi effect ensure that the spray of water mist is absorbed into the air. The fabric-covered swirl vanes further ensure that the air and moisture are thoroughly mixed. The fabric absorbs any extra moisture, giving it back when the humidifier is switched off. The water supply valve is controlled by a humidistat. This is a device which can measure humidity and operate a switch when a particular level is reached. It is measuring the humidity in the air conditioning duct. When the humidity falls below a predetermined level, the valve will open, and humidification will commence. The pack flow control valve may incorporate a mass flow controller, or it may be a separate unit. The mass flow controller is fitted to ensure that a constant mass flow of air is supplied to the air conditioning packs, regardless of the engine RPM or intake air pressure. This helps to make control of the aircraft pressurization much easier. When used with blower systems, the mass flow controller operates a spill valve, which dumps excess air to atmosphere. In systems that use engine bleed air, the mass flow controller adjusts the airflow through itself, so that the required mass flow passes to the system irrespective of changes in the value of the pressure upstream and downstream of the unit. The simplified mass flow controller shown here consists of a piston with cutouts in its face and barrel, which moves inside a cylinder with matching cutouts in its barrel. When the inlet pressure is low, the spring will push the piston fully to the left, and the cutouts in the barrels will be fully aligned, allowing maximum airflow through the unit. As the inlet pressure increases, the mass flow will tend to increase. However, the increased pressure on the face of the piston will move it to the right against the spring, reducing the airflow through the unit. Thus, with pressure changes, the piston position will modulate in the cylinder, maintaining a constant mass flow to the packs. Control of the pack outlet temperature is usually achieved by mixing hot air with the cooled air from the air cycle machine. The temperature control can be either manual or automatic. Automatic temperature control is achieved by comparing a pilot-selected temperature with the actual temperature of the air. In your aircraft, you will find that the selector does not have temperatures marked on it, but merely hot and cool. However, to aid understanding, we will mark our selector with temperatures. The temperature of a sensor in the cabin is compared electronically with a selected value, and any difference modulates the hot air valve to allow more or less hot air to bypass the cooling components to increase or decrease the cabin temperature. If, for instance, the pilot selects an increase in temperature, the hot air valve will open to warm up the cabin. Once the selected temperature is reached, the valve will modulate as required to maintain it. If the manual auto switch is moved to the manual position, the hot air valve will now move in direct response to the temperature selector switch position and remain in the selected position. The pilot is now no longer selecting a temperature. Instead, he is selecting the amount of hot air to be added. The cabin temperature achieved will vary with the environmental conditions. In order to avoid large temperature gradients between the extremities of the cabin, it is often necessary to divide the cabin into zones and control the temperature in each zone individually. This control is achieved from the flight deck using zone control knobs or switches. The larger the aircraft, the more zones there will be. The Boeing 747 has 5 zones, whereas the Airbus A320 has 3. The temperature of the air delivered by the packs is determined by the zone requiring the coolest air input. This will normally, but not always, be the flight deck. Individual zone requirements are satisfied by adding hot trim air from the bleed air system to the output of the air conditioning packs. The amount of trim air added is controlled by zone trim air valves. Their positions are dependent on inputs from the individual zone temperature control systems. The trim valve for the zone requiring the coolest air will be closed. The hot air pressure regulating valve modulates to control the pressure of the trim air. If required, this valve can be closed by a switch on the control panel. Most passenger transport aircraft supply warm air to the cabin by means of floor and wall passages, and this warm air maintains the interior surfaces at cabin temperature, reducing drafts and direct heat losses, which in turn allows the entering air temperature to be closer to the cabin temperature. Recirculation fans are used to augment the air conditioning packs, allowing a reduced number of packs to be used during the cruise, which decreases engine bleed requirements and improves fuel economy, while still maintaining a constant ventilation rate throughout the cabin. The fans draw cabin air from the underfloor area through filters, then reintroduce the air into the conditioned distribution system. Air from the areas around the toilets and galleys is not recirculated, but is vented directly overboard. The ducting is in 2 distinct sections, to provide for separate flows of cold and heated air. The cold conditioned air is supplied to the passengers individually, through a system known as the Gasper air system. Gasper air is tapped from one of the zone supply ducts upstream of where trim air is added. The Gasper fan provides a positive supply of conditioned air to all zones through individually controlled outlets or punka louvers. Conditioned air is supplied to the flight deck crew stations, where it can be adjusted for flow direction and quantity. It is also supplied to the flight deck windows for demisting purposes. The flight deck crew is able to monitor both the cabin and the duct temperatures throughout the aircraft. On the Airbus electronic screen air conditioning page, shown here, the zone temperatures are shown, as are the duct temperatures. The positions of the zone trim air valves are also graphically displayed. The crew also receives warnings in the event of malfunctions in the system. For instance, if the temperature of the air in the trim air duct becomes excessive, the amber fault light in the switch will illuminate. The vapor cycle air conditioning system is similar in operation to the domestic refrigerator, or the galley cart cooling system. That is the end of the lesson. You should now know that air conditioning systems may have a centrifugal water separator for use at low altitude, and a humidifier supplied with potable water for use at high altitude. You have seen that the mass flow controller ensures that the air conditioning packs receive a constant mass flow of air throughout their operating envelope. You should know that the cabin is split into a number of zones, and that the outlet temperature of all packs is set by the zone requiring the most cooling. Zone trim valves add hot air to the other zones to satisfy their requirements. Recirculation fans are used to augment the air conditioning packs, and the Gasper system supplies cool air to individual seats. Finally, you should have learned that on some smaller aircraft, a vapor cycle air conditioning system is used. In this lesson, we will examine the pressurization control systems fitted to modern airliners. We will look at the necessary safety devices fitted and the indicating systems available to the crew. Modern aircraft operate more efficiently at high altitudes, and they have high rates of climb and descent. In order to take advantage of these properties, the interior of an aircraft flying at high altitude is pressurized to allow passengers and crew to function normally without the need for additional oxygen. Up to an altitude of 10,000 feet, the air pressure, and consequently the amount of oxygen, is sufficient for humans to operate without too many problems. However, the effects of lack of oxygen can become apparent at altitudes above this. To prevent any risk of problems due to a lack of oxygen, it is a regulatory requirement that cabin pressurization systems are designed to produce conditions equivalent to a maximum of 8,000 feet in the aircraft cabin. This means that there is no need for oxygen equipment except for emergency use by crew or passengers. The difference in pressure between the pressurized hull and the atmosphere produces stresses, which are applied cyclically every time the aircraft is pressurized and depressurized, causing fatigue, which can ultimately lead to structural failure. The airframe structure must be strong enough to withstand the differential pressures generated. The aircraft manufacturer will set as a structural limit a maximum differential pressure. That is, the difference between the pressure inside the pressurized compartment and the pressure of outside air, which the pressurized hull can safely withstand. The normal operating maximum will be slightly lower than this. On modern transport aircraft, the normal operating maximum differential pressure is typically between 8 and 9 pounds per square inch, or psi, or between 552 and 621 hectopascals. This maximum differential pressure, along with the maximum permitted cabin altitude of 8,000 feet, will set a maximum for the altitude at which the aircraft can operate. As you can see from this barometric pressure table, the air pressure at 8,000 feet is 10.91 psi. So if the manufacturer has set the aircraft's maximum differential pressure at 8.2 psi, then the minimum outside pressure is 10.91 minus 8.2, which equals 2.71. We can see from the chart that this equates to just a touch over 40,000 feet. Thus, an aircraft with a maximum differential pressure limit of 8.2 psi will have a maximum operating altitude of 40,000 feet. This is, of course, the pressurization limit. The aircraft's maximum altitude may be further limited by other factors. If the maximum permitted differential pressure is reduced by an aircraft defect, for instance, a cracked cockpit window, the maximum aircraft altitude will also be reduced by the need to maintain the maximum cabin altitude at 8,000 feet. For instance, if the maximum differential pressure is reduced to 6 psi, then the minimum outside pressure will now be the pressure at 8,000 feet, which is 10.91 psi minus 6, which equals 4.91 psi. From the table, the altitude equal to 4.91 psi is approximately 27,000 feet. This is the maximum altitude limit with a differential pressure of 6 psi. The passenger cabin, flight deck, and cargo compartments are normally pressurized. The landing gear bays, radome, and the tail and nose cones are unpressurized. Cabin pressurization is achieved and controlled by having a constant mass flow of air entering the cabin from the conditioning system, and then varying the rate at which it is discharged to atmosphere. The constant mass flow of air is supplied by the air conditioning packs via their mass flow controllers, and is discharged to atmosphere through the discharge or outflow valve or valves. The position of the outflow valve can be controlled either automatically by an automatic pressurization controller or manually by the flight crew. Closing the outflow valve reduces the outflow and increases the cabin pressure, causing the cabin altitude to descend. Opening the valve has the opposite effect, increasing the outflow, reducing the cabin pressure, and causing the cabin to climb. There are a number of safety devices which must be fitted to any cabin pressurization system. The safety valve is a simple mechanical outwards pressure relief valve, fitted to relieve positive pressure in the cabin when the normal maximum pressure differential allowed for the aircraft type is exceeded, preventing the structural limit from being exceeded. This valve is totally independent of all other control systems, and will open if the cabin differential pressure rises to approximately 0.25 psi above the normal maximum. The regulations stipulate that there must be 2 safety valves fitted. The fuselage is designed to withstand the positive differential pressure produced by the pressurization system. However, it is not able to withstand the crushing forces that a negative pressure differential would produce. To prevent this problem, simple mechanical inwards relief valves are fitted. They will open if the pressure outside the aircraft exceeds that inside by 0.5 to 1.0 psi. There must also be 2 of these valves. The inwards and outwards safety valves may be combined together in one unit, or may be completely separate components. They are positioned above the aircraft flotation line, so that in the event of a landing on water, they will not allow the water to flow into the aircraft. The dump valve is a manually operated component. It enables the crew to reduce the cabin pressure to 0 for emergency depressurization. This valve may, in some systems, also be used as the air outlet during manual operation of the pressurization system. Blowout panels are fitted in the floor between passenger and cargo compartments, in order to prevent excessive differences in pressure occurring between these areas in the event of, for example, a cargo door opening in flight. The panels are normally fitted under passenger seats, and they are held in place by springs. If a cargo door should open, then the pressure differential between the passenger and cargo compartments will overcome the springs and the panels will open, equalizing the pressure between the compartments before the floor structure is damaged. Some systems are fitted with a ditching control, which will close all the discharge valves in the event of a forced landing on water. This will reduce the flow of water into the cabin. There will be an oral or visual warning if the cabin altitude exceeds 10,000 feet. The oral warning may take the form of a horn, and the visual warning a red light in prominent view of the pilot. There is normally a horn cutout button which can be depressed to cancel the horn. That is the end of the lesson. You should now know that the maximum permitted cabin altitude is 8,000 feet, and that the normal maximum positive differential pressure is between 8 and 9 psi. You should understand that the aircraft's maximum operating altitude is dependent upon the maximum differential pressure, and given a barometric pressure table, you should be able to calculate this maximum altitude. You should also know that the pressurization is controlled by having a constant mass flow of air into the fuselage and controlling its exit using outflow valves. You should understand the purpose of the various safety devices fitted to a pressurization system. The positive outward opening pressure relief valves prevent the structurally limiting maximum differential pressure from being exceeded, and negative inward opening relief valves prevent the pressure inside the cabin becoming less than that outside. The dump valve is used to completely depressurize the aircraft, and the ditching control is used to close all outflow valves prior to the aircraft landing on water. Blowout panels are fitted in the floor between passenger and cargo compartments in order to prevent excessive differences in pressure occurring between these areas. And finally, an oral or visual warning will be given to the crew when the cabin altitude exceeds 10,000 feet. In this lesson, we will examine the various types of controllers used by pressurization systems. We will look at the required pilot inputs and at the indicating systems used to inform the crew of correct system operation. We will look at a typical flight profile using an automatic pressure controller. And finally, we will see how the pilot can control the pressurization manually. Pressurization controllers vary in construction and operation. On simpler, small aircraft, they may be purely pneumatic in their operation. On old generation jets, they are electro-pneumatic. And in the case of most modern aircraft, they are electronically operated. Whatever type of controller is used, it will receive signals informing it of both the cabin and ambient pressures. The controller has three functions. It will control the cabin altitude. It will control the cabin altitude rate of change. And it would limit the maximum differential pressure. Old generation controllers have controls for selecting the required cabin altitude and cabin altitude rate of change. They send signals to the electric motor-driven outflow valves. On modern aircraft, most of the control is done automatically by an electronic controller. The controller receives electrical signals proportional to aircraft altitude and cabin altitude. It will then control the outflow valves to maintain a cabin altitude according to an inbuilt program. On the Boeing 737, the pilot selects the aircraft cruise altitude and landing airfield elevation during his pre-flight preparation. The controller automatically controls the outflow valve to achieve and maintain the appropriate cabin altitude for the phase of flight. On most Airbus types, during normal operation, the pilot makes no inputs to the system at all. The controller receives all necessary altitude data from the flight management computers. This schematic diagram shows the arrangement of the pressurization control system of a modern passenger transport aircraft. The automatic controllers are duplicated and have inputs from the aircraft static pressure sensing system, the cabin pressure sensors, and the air-ground logic system. If pre-pressurization, that is, pressurization on the ground prior to takeoff, is part of the schedule, then inputs are also required from the thrust lever positions. One controller is operating and the other is on standby. The roles are automatically reversed after each landing. In the event of a failure, the standby controller will automatically take over control. The controllers are normally located away from the flight deck in an electrical service centre. Each outflow valve is operated by one of 3 electric motors. There is one motor for each automatic controller and another for manual control. The minimum indications required for a pressurization system are cabin altitude, cabin vertical speed, and cabin differential pressure. This information can either be presented on direct reading gauges or electronically on an LCD screen. The cabin altimeter measures cabin pressure, but it is expressed on the gauge in terms of the equivalent pressure altitude of the cabin. The cabin vertical speed indicator, VSI, indicates the rate at which the aircraft cabin is climbing or descending. The cabin differential pressure gauge indicates the difference between the air pressure inside the cabin and the outside air pressure, and is generally calibrated in pounds per square inch. In the event of a malfunction of the pressure controller or outflow valve, a high pressure reading on this instrument would indicate that the safety valves were controlling the cabin pressure at the structural maximum pressure differential. The cabin pressurization control panel is remote from the pressurization controller and will generally be fitted in the overhead panel on the flight deck. The control panel may have rotary knobs for the pilot to set the expected cruise altitude and the elevation of the landing airport. In a typical system, there are 3 modes of operation: auto, alternate, and manual. In auto mode, one of the 2 automatic pressurization controllers will be operating. The pilot can force the system to use the other controller by selecting alternate. Selection of manual will lock out all normal automatic functions and enable the pilot to control the position of the outflow valves. We will now take a look at a typical flight to see how a typical pressurization system will operate in the auto mode. During his pre-flight preparation, the pilot will set the expected cruise altitude and the landing airfield elevation. In our example, the aircraft will be cruising at 30,000 feet, before landing at an airfield with a pressure altitude of 1,000 feet. The automatic controller will climb the cabin to the minimum altitude required to maintain the maximum permitted differential pressure at the cruising altitude. If the maximum permitted differential pressure for this aircraft is 8.0 psi, to what height will the cabin climb? To the nearest 500 feet. Enter your answer and click on Submit. With the aircraft on the ground, the operating controller will hold the outflow valve fully open. When the pilot opens the thrust levers for takeoff, the controller will signal the outflow valve to move towards closed, pre-pressurizing the aircraft cabin into a small differential pressure of approximately 0.1 psi. This ensures that the transition to pressurized flight will be gradual and that there will be no surges of pressure on rotation. As the aircraft takes off, the ground air logic system will signal the controller to switch to proportional control. The controller will sense ambient and cabin pressure and position the outflow valves to control the rate of cabin pressure reduction, or cabin climb, in proportion to the rate of climb of the aircraft. so that slightly less than the maximum permitted differential pressure is attained as the aircraft reaches its cruising altitude. The cabin rate of climb will normally be between 300 and 500 feet per minute, with a maximum limit of 500 feet per minute. If the aircraft is required to level off during the climb, then the pressurization controller will sense this and level off the cabin. When the aircraft begins to climb again, the controller will once more position the outflow valves to control the rate of change of cabin altitude, in proportion to the rate of climb of the aircraft. The cabin rate of climb will again normally be between 300 and 500 feet per minute. When cruise altitude is reached, the controller will maintain a constant cabin altitude. There will now be a constant mass flow of air through the cabin. The mass of air coming in from the packs will equal the mass leaving through the outflow valve. Once established in the cruise, small changes in aircraft altitude will be accommodated without any change in cabin pressure. However, if the cruise altitude has to be increased significantly, then the flight altitude selection will have to be reset. If this is not done, and the maximum differential pressure is reached, the controller will not allow further increase in differential pressure, and the aircraft will now be in maximum differential control. As the aircraft climbs, the cabin will also climb to keep the differential pressure within limits. When the controller senses that the aircraft is descending, it will switch back to proportional control and descend the cabin at a rate to produce a differential pressure of approximately 0.1 psi on touchdown. The descent rate will normally be about 300 feet per minute. When the aircraft lands and the ground air logic system switches to ground mode, the outflow valves will slowly open fully to equalize cabin and ambient pressures. On older types of aircraft, the cabin is not pressurized prior to takeoff. And, because the fuselage is not designed to absorb the landing shock simultaneously with pressure differential forces, the cabin is completely depressurized just prior to landing. With the system under manual control, the outflow valve position can be adjusted by operation of the manual open-close switch. The pilot now controls the differential pressure, cabin altitude, and cabin rate of climb or descent. On the system shown here, a placard along the bottom of the control panel shows cabin altitude against aircraft altitude at maximum differential pressure. The pilot can consult this in order to establish the cabin altitude required for any given aircraft altitude. Opening the outflow valve will cause the differential pressure to decrease, the cabin pressure to decrease, and the cabin altitude to increase. The cabin VSI will show a climb. Closing the outflow valve will cause the differential pressure to increase, the cabin pressure to increase, and the cabin altitude to decrease. The cabin VSI will show a descent. Cabin rates of climb and descent should be carefully monitored and should not normally be allowed to exceed 500 feet per minute during the climb or 300 feet per minute in the descent, in order not to cause too much discomfort for the passengers. That is the end of the lesson. You should now understand the relationship between cabin pressure, cabin altitude, and ambient pressure. Remember, in level flight, if the outflow valve is opening, the cabin vertical speed indicator will show a rate of climb, the cabin altitude will increase, and the differential pressure will decrease. If the cabin altitude reaches 10,000 feet, then an oral and/or visual warning will be given to the crew. Similarly, in level flight, if the outflow valve is closing, the cabin VSI will show a rate of descent, the cabin altitude will decrease and the differential pressure will increase. If the maximum differential pressure is exceeded, then the positive pressure relief valves will open. Finally, remember that if the pressurization system is in the manual mode, the cabin altitude, the cabin rate of change, and the differential pressure are all controlled by the pilot operating an outflow valve manual open-close switch.